Hello, here we go. Discrete probability theory. So this video will be a little longer. There's quite a bit of material in here, so make sure you spend a fair amount of time working through the exercises and such. But here we're going to talk about what's called discrete probability theory. So here's a definition. So a probability function, right, assigns to each outcome x, right, in a sample space S, a number p of x, so that it's between 0 and 1 for all x in S, and that if you add up the probabilities, you get 1. In other words, so if you think about the good example is flipping a coin, right? Flipping a coin, heads or tails. So there would be two outcomes. The probability of both of them is typically considered to be equally likely. So they both, probability of getting a head would be 1, probability of getting a tail would be, 1/2 and 1/2. So they add up to 1, etc., etc. So here's an example of something here. Okay, suppose that a die is loaded, right? So that the number 2 through 6 are equally likely to appear, okay? But that 1 is 3 times as likely as any given number to appear, okay? So that's kind of a weird, I don't think such a die actually exists in the real world. You can think about that, but okay, let's assume it does. To model the situation, we should have, here it is. I was just rewriting this. Probability of 2 equals the same as 3, 4, 5, and 6, but the probability of 1 is 3 times the probability of 2. Okay, so that's really rewriting this scenario down. And since we need 1 to be equal to the sum of all of them, we can write this down and notice that 1 has to be equal to 8 times the probability of 2. Solving, just dividing by 8 gives us the probability of getting a 6, right, or a 2, that is, or 3 or 4 is 1/8, right? And then we can calculate that the probability of getting a 1 must be 3 times that, or 3/8. So that's kind of a weird example. I really... You should think about that example. I don't think that exists. Anyway, long story. Okay, so the probability of an event, right, E, is defined as the sum of the probabilities of the outcomes in E. In other words, so an event can be much more elaborate than just one event. I mean, one outcome, right, of an experiment. It can be like, you'll see some examples here. So here we go. So given the assumption of the previous example that we just went through, right, what is, the probability of an odd number is, right, well, that'll be, you take the probability of getting a 1 plus the probability of getting a 3 plus the probability of getting a 5. So it's 5/8. Okay, so and that's with an unfair die, of course. That's why it's larger than 1/2, right? Right. Okay. So for a fair die, what would it be? Well, with a fair die, you would have that the probability of getting any number would be the same. It would be 1/6, right? So if this were a fair die that we were talking about, then the probability of getting an odd number would be 1/6 plus 1/6 plus 1/6, 3/6, or 1/2, since half the numbers are right. Odd and half are even in that collection. Okay, here's a theorem. Here we go. So let E be an event. The probability of the complement of E, in other words, has to satisfy that the probability of E plus the probability of the complement of E, or the opposite of E, has to be equal to 1. And here's a little proof, right? If E is the event that contains all these outcomes, and E, the complement, is all the rest, then we know the probability of E would be you add all those up, right? And the probability of the complement would be you add up the probabilities of all the things in here, these events. And when you add them together, look, you're adding up the probability of all of the elements. We know that's equal to 1, okay? So sometimes when you're interested in knowing the probability of an event, you look at what the complement is, and that's how you would do it. So this is probably an example. Here we go. Let's take a look at this. Example 6.6.6. Okay, so remember this. 5 microprocessors are randomly selected, right, from a lot of 1,000. We've talked about this. Among which 20 are defective. So in this previous example, we found that the probability of obtaining no defective microprocessors was, 0.999, whatever that is, right? So by this theorem, the probability of obtaining at least one defective microprocessor is, well, you take 1 minus that number. Okay, so that's how this can be done. Okay. All right, let's look at this problem. Here's a famous problem that you may have come in contact with if you've been in a classroom, I guess. It's really a little bizarre. So here's the problem. Birthday problem. Find the probability that among n persons, at least 2 people, right, have birthdays on the same month and date, not necessarily the exact same year, right? So assume that all months and dates are equally likely and ignore February, okay? So we have February 29th birthday, so we ignore that, right? Okay, like in other words, the leap year. So here's a solution. So we just look at this, right? And so let's let E be the event that at least 2 people have the same birthday, right? Okay, so then the complement of that is the event that no people have the same birthday, right? Okay, so what we're going to do is we're going to calculate probably the other one, right? So here we go. Let's take a look at this. So let me just read it here. I'm sorry about that. Since all months and dates are equally likely, we ignore February 21st, blah, blah. The first person's birthday can occur on any one of 365 days, right? Correct. Now, if no 2 people have the same birthday, the second person's birthday can occur on any day except that day, right? So there's 364 to choose from. Similarly, the third person, et cetera, et cetera. So you keep going, right? So if it follows that the size of the event, no 2 people have the same birthday is, so you just do this. You take 365 times 364, right? Okay. Now, in this theorem, the probability that at least 2 people have birthdays on the same month, right, and date would be 1 minus that number divided by, well, 365 to the n, because that's all the possible, right, events. Now, then, so here's the odd thing. What you do is this number can be calculated. So for n equals 22, right? So if we have 22 people, you plug that in here. The probability is 0.47. And for n equal 23, the probability is 0.50. So that's why that if you're a betting man, right, and you have more than 23 people in a room, since the probability is greater than 1/2, you would expect that 2 people would have the same birthday date, not the same exact birthday. Okay. All right. So what is this? If E1 and E2 are events, the event E1 union E2 represents the event. Yeah, that should be good. E1 or E2, right? Or both. And the event E1 intersected with E2 represents the event E1 and E2, right? Okay. So let's just take a look at this this theorem here. This is so let's let E1 and E2 be events. Then the probability of E1 or E2 is equal to the probability of E1 plus the probability of E2 minus the probability of E1 intersected with E2. And then the reason for that is, if you just think about, well, here's the proof of it, you can see it, but you have to subtract out the events that you're that are occurring twice in this first sum, and that can be seen right here, right? So here we have it. So if you look at this diagram, here's sort of a diagram of, E1 might have these first I events right here. E2 might have these occurrences in the space, and here's the ones in common, right? So if you just add them up, if you want to know what E1 union E2 is, you have to add up, right? you add up everything in the union, but you have to subtract off the ones that occur twice, right? And there you have it. Okay, let's take a look. Oh, then there's this idea, like if E1 and E2 are mutually exclusive events, in other words, if they share no outcomes in common, well, then the probability of E1 union E2 is just the probability of E1 plus the probability of E2. Because in this calculation we did up here, notice that there's nothing in common, so that would be go to 0. So there's an example of that. Oh, here we go. Here we go. 2 dice. Let's just go through some examples now. 2 fair dice are rolled. Find the probability of getting doubles or the sum of 5. Okay, so here's sort of the solution, right? You look at it. So let's let E1 denote get doubles, okay, and E2 denote the event get a sum of 5. So you can calculate the probability of E1, right? There's 6 different doubles. It's 1/6, right? And then you just write down how you get 5, and there's 4 of them, right? It's 1/9, right? So by this corollary, right? Corollary 6.611. So by this thing, notice if you look at those two things, there's nothing in common. You can't get doubles and add up to 5. So we get the probability of getting doubles or getting a 5. You just add them together, and it's 5/18. Okay. Okay, let's take a look at this example here. So let's see, where are we here? Okay, here we go. So 2 fair dice are rolled. Find the probability of getting doubles or a sum of 5. So we did this problem, right? Now let's take a look at this. Here's a figure, right? Let's suppose that we roll 2 fair dice, right? And since each outcome is assigned the value 1/36, forget the dots that I've drawn here, right? The probability of getting a sum of 10 is 1/12. So if you look at getting a sum of 10, right, well, you can just add it up, like what adds to 10, right? You get, there's 1/12 of them. So if if at least one die shown is a 5, right, and then if you look at this blue thing, that defines, in a sense, a new sample space, right? So the shaded outcomes become a new sample space, and each shaded outcome is represented the value 1/11 because there's 11 possibilities, right? So the probability of getting a sum of 10, right, given that at least 5 occurs, is 1/11. So what we're talking about here is this idea of conditional probability, okay? So let's suppose that we roll 2 fair dice, and I think, well, we just sort of went through this example here. Right now, let's discuss conditional probability in general. So we let this symbol here, let probability of E given F, denote the probability of E given F. So F is something that we think of as occurred, right? In this situation, F becomes a new sample space, right? Since values of the outcome in F originally, right, sum to the probability of F, right, etc. So we can change the value of the outcomes of F by dividing by P. So here you have it, right? So the summary assigns the value of the outcome in P intersected with F. So you divide out the F, and you get this is the correct answer, right? So here we go. Let E and F be events, and assume that the probability of F is greater than 0. So the conditional probability of E given F is, well, here's our symbol, but you take the things that occur in E intersected with F, that sort of, think of it it counts up the number of things that are in the event that are also in F, and you divide by the probability of F so that, it makes sense, right? So this definition, to compute the probability, to get the sum of 10, here in our example, basically do this. Here's a solution of this example, but just using the conditional probability idea. So here we go. Solution. Let's see. In definition, let's use this definition right here to compute the probability of getting a sum of 10, given that at least one die shows a 5. when 2 fair dice are rolled. Okay, so here's the solution. We have to calculate a couple of things here. So let E denote the event getting 10, and let F denote the event at least 1, 5. So if you look at that, the probability of E intersecting with F is 136, because there's only one choice. If we know how that we have a 5, there's only one, 5 plus 5, right? So since 11 outcomes belong to F, right, we know that, then we know that the probability of getting F is 1136. So to reconfirm our intuition with the example, therefore the probability of getting 10, if you know that have a 5, is you take 136 divided by 1136 and you get 1/11th. Okay, so here's another example. Weather records show that the probability of high barometer pressure is 0.8, and the probability of rain and high barometric pressure is 0.1. Use the definition, right, of conditional probability. The probability of rain given high barometer pressure is, well, so you can use this formula this way, right? We take the probability of rain and high barometric pressure divided by the probability of high barometric pressure, and you get 0.125. Okay. So, all right, now let's talk about independent events. So what is an independent event? Okay, well, so if the probability of an event does not depend upon event F, so if 2 events don't influence the probability of the other event F, in the sense that here the probability of E given F is the same right here as the probability of E, then we say that E and F are independent events. So by the definition that we just had here, right, the probability E, right, given F is the probability of E divided by this formula. Thus, if E and F are independent events, right, then you can actually just say that that's the same as the probability of E, okay? Or that the probability of E, so now if you use this formula, the probability of E and F turns out to be just the product. If you just multiply, that's kind of interesting thing about this definition, you just put the 2 together. And so independent events have this nice property that if you want to calculate the probability of E intersected with F, that they both occur, it's just the product of their probabilities, as you see here, as long as they're independent events. Okay, let's look at this example here. Okay, here's a good independent events. If we flip a fair coin twice, okay, the outcome of the second toss does not depend upon the outcome of the first toss, right? Okay, so for example, if H is the event heads on first roll and T is the event tails on second roll, we expect that the event H and T are independent. Using this definition to verify that H and T are indeed independent. Okay, here's a solution. Since H intersect T is the event heads on first toss and tails on second toss, right? Thus, the probability of H intersect T is 1/4, since the probability of H is 1/2, right? You can see that, in fact, yep, it worked out. It is the product. Therefore, the events H and T are independent. And you get the 2 different answers by looking at the actual table. You can see that there's 1 in 4 chance right here that you get a heads by just making a sample space. Okay. All right, let's move on to this next thing. And this is a very important part of probability theory. It's also very useful. It's under the heading of pattern recognition and Bayes' theorem, okay? So here's how this is used is essentially this way. You talk about features typically, based on features of an item. Okay, so let me go through this example. So here, pattern recognition. Okay, so place items into various classes based on features. Okay, so of the same items. So, for example, this is a good example. Wine might be placed into the classes premium, table wine, and swill based on features such as acidity, bouquet, whatever it might be, right? So one way to perform such a classification uses probability theory. So given a set of features F, okay, one computes the probability of a class given F for each class and places the items into the most probable class, right? That is the class C chosen is the one for which the probability of C given F is greatest. So here, let me do this example. So let's let R denote class premium. So there's premium, T denote table wine, S is swill, right? And suppose that a particular wine has feature set F. Okay, so you got this feature set S, right? And let's suppose that we have the probability that it's R is 0.2 if it's given that feature. Right? So you have these numbers. Now, since class table wine has the greatest probability, right? This wine would be classified as table wine. So you could use this idea, what we're getting at is to try to classify things based upon probability theory. Okay, so here's this really famous and useful theorem, which I will just state, and you can look at it, and it relates the following ideas that if you have these, so suppose that the possible classes are, you have n classes, okay? Suppose further that each pair of classes is mutually exclusive to each, and each item to be classified belongs to one of the classes, right? For a feature set F, we have, and there's this formula which looks very involved, but it's really not that bad. We'll do some examples. That the probability of class J, given those features, is this, okay? All right, so here's the proof of it. It's just a matter of chasing through the definitions that we've developed and seeing that it works out correctly. But let's look at this example. This is kind of a good example. So we have this theorem, right? And here's this scenario. So we have telemarketing, right? So at a telemarketing firm, cell phone, I guess that's the name of the firm, we have Dale, Rusty, and Lee make calls. The following table shows the percentage of calls each caller makes and the percentage of persons who are annoyed and hang up on them. So, okay, so let's look at the table. Dale makes, 40% of the calls, right? 25 and 35. Does that add up to the right number? Yes, okay. So Dale makes the most calls. Let's see. The percentage of hang-ups, 20% hang up on Dale, right? 55% hang up on Rusty, and 30% hang up on Lee, right? So let's just go through it. Let's calculate all these probabilities, right? So let D denote the event Dale made the call. Let R represent the event, right? Rusty made the call, and let L denote the event that Lee made the call, right? And let H denote the event the caller hung up, right? So we're interested in like the hang up thing there. Let's see if we can actually find all these probabilities, right? The probability of D, the probability of, all these different things. So here's the solution. We'll just sort of run through it. So you use the different information. Let's see here. So Dale made 40% of the calls, so that means that the probability of, right? Dale made the call is 0.4. Similarly, from the table, we can get the probability of R and the probability of L. That comes right from the table, right? Okay. So now let's take a look at this. So it says, given that Dale made the call, the table shows that 20% of the persons hung up. Therefore, the probability that a person hangs up, H, given that Dale made the call, is 0.2. That's it. It comes from here, right? 20% or 0.2. Similarly, we have, so that gave us that quantity. Similarly, we can find the probability that the caller hangs up given Rusty calls and here. So we're slowly going through here. Now, to compute the probability that Dale made the call given that they hung up, right? Notice here we're trying to calculate. We're changing the roles of given the person hung up. We want to know how did Dale make the call? Well, if you write down that theorem and you go through, you find out that's point, right, 248. And similarly, right, you can calculate the probability that. So you got this calculation, right? You can calculate all this thing. Again, using Bayes' theorem, we notice that, okay, the probability that Dale made the call plus the probability that given they hung up, plus the probability that R made the call given they hung up, plus the probability that, what is his name, Leo or Leon, well, made the call given that they hung up is 1. So we can now use this equation and we can obtain the probability that Lee made the call given that they hung up, right? So finally, and this is we can see that the probability that the person will hang up, right, is equal to, boom, we just go for it. We just write all down the theory is 0.32. So it's kind of an interesting way, like if you have a mixture of people doing certain aspects, you can see that you can calculate the probability that the person's going to hang up, and it's slightly higher than if Lee and Dale made calls. So you might say, well, it's fire Rusty or something. I don't know. And then lower the number. Okay. And so there's another example. But anyway, there's a lot of nice exercises in here for you to look at. And I hope I've illustrated to you how to use these tools. You're going to have to work on this and get used to some of these calculations, I think, if you're not familiar with it. So anyway, thank you. Bye-bye.